Hey guys, just a quick word before the presentation. To follow along with the practical tutorial at the end, um, make sure you've got VirtualBox downloaded and installed. Make sure you've secured a nice super legit copy of a Windows 7 ISO somewhere from the internet. So yeah, create your fresh Windows 7 virtual machine. If you don't know how to do that, follow the tiny URL link there. Once you've got your VM installed, install Immunity Debugger. Follow the link, install, we're going to be using Sublime Text. You can use whatever text editor you prefer. Make sure you install 32-bit Python 2.7. That link right there should do it. And if you can't be bothered typing out all those links, grab the paste bin link down the bottom and you can copy past them because you're lazy. Cool.
Okay, cool. All right. So, hello everyone. Um, my name is Viren, and I'm a manager in Deloitte Cyber Risk Advisory Practice. And today I'll be talking about Exploit Development 101, and it'll be an introduction to binary exploitation. But specifically, we'll be looking at writing exploits, buffer overflow exploits in 32-bit applications from scratch. So how do you go about identifying a buffer overflow vulnerability in an application? And what can you do to weaponize that whole situation into a working exploit? So what we will hopefully be able to do at the end of this presentation would be, you would have written, hopefully, your first exploit, which will be popping calculators. So nothing more exciting, but it all depends on your imagination. So you can do whatever with it. So a little bit about me. So my name's, as I said, Viren. I am currently working with Deloitte in the cyber risk advisory practice, specifically cyber attack and response. So cyber attack and response is a team that does penetration testing and incident response style of work as well. So not only do we attack, but we also respond to attacks. I'm based out of Sydney, but my colleague here, Gabriel, I don't know if any of you know her. So she works in the Melbourne practice, one of our absolute rock stars. Yeah. And so, yeah, like I said, I'm a manager in the practice. You can reach out to me on Twitter, or you can look at my blog. So just a heads up, like if there are a few questions that you have, which I'm not answering today, or if you have any other questions in the next few days, you can reach out to me on Twitter, or you can reach out to me on LinkedIn. Choose your poison. Don't reach out to me on Facebook because, yeah, nah, that doesn't work. Cool. So yeah, before we begin, just wanted to give you a, reality or expectation match or mismatch. So if you're expecting that in 2 hours' time, you'll become an expert in, identifying buffer overflow exploits and actually writing and like a whole exploit from scratch, you're gravely mistaken. It's not like this whole presentation, although it's 2 hours, but it's not a white paper. So what the objective of this presentation is to sort of break the barrier or break the glass that, exploit development is not that creepy. It's not like, you have to just give up on your life and, spend it on studying. It's not that complex. It doesn't have to be that complex either. So this presentation would sort of be a, like a benchmark. So I don't know if any of you guys, like how many of you guys, like you people actually go to the gym. So this is like a 1 rep max, all right? This will be your 1 rep max. So something like the maximum rep that you can do sort of to, trick your brain into understanding, okay, this is my limit and this is what I have to work towards, all right? So this is your 1 rep max. I will answer questions. So like if you've got any questions, just stop me at that point, ask it at that time, and I will choose to answer or not answer those questions. So the reason why I say non-answer, I will explain, all right? So the reason why I say that I will choose not to answer that question is because, in my opinion, if that question or the pursuit of the answer to that question would lead to something really interesting, or you will learn a lot from that question, then I will let you suffer on that question, okay? And I will tell you this like from personal experience, and I'll actually share a personal experience as well. Um, how many of you actually know anything about instructions, assembly instructions? Cool. What do you know about NOPs? Yeah, nice. Yeah, but what NOP sled? What is NOP? Yeah, that's correct. So okay, so right, so no operation, perfect. But at this stage of our evolution of as a human race, computers haven't actually gained consciousness. So when you say no operations, well, computer doesn't understand no operation. So what does that mean? Well, computers like us human beings cannot slack off, right? So it actually performs an instruction. Not performs an instruction, but it's so meaningless that it actually does nothing. So you wouldn't even see what it does. But if you look it up, it'll actually do exchange EAX, EAX. So it actually performs that instruction, but it's so meaningless that you don't see any change. And that's what NOP's essentially meant to do. Do nothing but kill time, right? So that was something that I learned because I actually couldn't compute. Like this thing didn't sort of go well with me. I'm like, okay, well, no operation, but surely computer doesn't understand what no operation is. So what is it? So that whole pursuit of that answer to my question led me to this very interesting article. So yeah, so the moral of the story, if you've got a question which can be a learning opportunity, I will choose not to answer it. And if you want to think that I don't know the answer to that question, yeah, you're free to judge, but you know, just a bit of expectation match. All right, so before we begin, just you know, a few common terms that we'll be using in today's presentation and in general. So fuzzing is an art of providing invalid or unexpected or random data as an input to a field. Now, the reason why I say that fuzzing is an art is because writing, you know, exploits or buffer of like an actual exploit is easy, but finding that crash point and finding whether or not it's exploitable is actually an art. So that's why I say fuzzing is an art, and anyone who's actually done quite a lot of, you know, writing exploits, I would say they're nothing short of artists. Like they deserve all the kudos for it. And also, like what today we're going to do is we're also going to do fuzzing, and we will be, or we'll force the application with overly long inputs and just see how the application handles that input. And then we'll monitor, or we will monitor the application crash in like a debugger. All right, so when I say crash, what I mean is crash is an ungraceful termination. So whenever you hit Alt F4, the whole process dies. So unlike Linux, Windows actually treats or gives respect to process, and that's why it makes sure that everything's going down perfectly. But crash would be an ungraceful termination. So anything that, you know, the standard error message that you get that the process quit ungracefully, or, you know, like well, the general pop-up that you get from Windows which says send crash details to some server. So yeah, so that's the crash that we'll be looking at, or we'll be hammering the application until we get that crash point. Cool. Buffer overflow occurs when a program attempts to write data more than the buffer can hold. So what happens is, like if you're looking at a classic stack-based buffer overflow, when you give it a specific field input or field length, and if you give it more input, then it'll actually start overwriting other areas of the stack, and that's something that we'll be exploiting today. There are other forms of buffer overflows as well, which is like heap-based buffer overflows and off by one error. I'm pretty sure few of you here would have run into this problem, off by one. So off by one error buffer overflows are basically the usage, or there's a difference between less than and less than or equal to. So I know there are people who actually use that interchangeably, but it's actually not the same. And that could lead to buffer overflow situations as well, off by one. So those are exploitable as well. The thing that you can do with a perfectly good exploit for buffer overflow, you can actually do remote code execution, which we'll be hopefully doing that today, or we could cause denial of service. So in many ways, one goes hand in hand. Sometimes you just have to kill the process to make it spawn another process. Or if the application actually manages that pretty well, then you can have a separate process or a separate thread spawning from the main process. You can also do authentication bypass type of attacks as well. You can look it up. There are sort of FTP-based exploits that have actually bypassed authentication straight up. You land into whatever that FTP server has to offer. Extremely hard to find and even harder to exploit. That is definitely true. You would basically need to spend hours just looking at a piece of software with a decent size to identify this particular vulnerability. So yeah, it's pretty hard. And if you go into situations where you have to do SEH bypass, which is structure and error handling bypasses, or ASLR bypasses, that it actually gets tricky really hard, really fast. So exploit. I will probably be using these two terms, or basically just one term in two different ways a lot. Exploit as a verb, as Oxford Dictionary would say, make full use or derive benefit from, which in our case we will be exploiting a vulnerability. So we'll be making use of a vulnerability in the application to perform an unintended or an unfair action. So we'll be making a software pop a calculator in today's workshop. And exploit as a noun is also a piece of code that you are going to write. So you will be writing an exploit that exploits a buffer overflow vulnerability. Does that make sense? Cool. All right, so moving to 32-bit. Now, 32-bit CPU or 32-bit processor is basically a type of CPU architecture that transmits or handles 32 bits of data in a clock cycle. So as our friend mentioned or touched upon clock cycles, yes, so 32 bits is the amount of information a CPU can process every time it performs an operation. Now, if you look at the history of 32-bit, I know I think everyone here actually uses 64-bit OS or a 64-bit processor. So, but back in the day, I'm talking about my uni days, which was, anyone wants to take a guess? It's more like 20 years ago. No, not that old. 10 years ago, I actually essentially used Pentium processors. So those were 32-bit processors with 32-bit operating systems and 32-bit applications. So how many of you actually think that 32 bits very synonymous to x86? Or have you heard the term x86 before? Okay, so who thinks they're synonymous? Cheers, cheers. All right, cool. Well, you are right in the sense, well, what Microsoft essentially wanted you all to believe. So if you look at your C drive, you will see program files x86, and then you will see program files. So one of that is actually 32-bit. Actually, yeah, tell me, why do you think there are two program files in your C drive? Oh, that's actually the other way around. Yeah. Okay. Cool. Um, good one. Good one. All right. So what essentially 64-bit the Windows does is it's actually emulating a compatibility layer for Windows 32. So they've got something called Windows 32-bit on Windows 64-bit, and that's WoW 64. So what it essentially does, it provides a emulation environment for 32-bit applications to run on 64-bit OS and by extension 64-bit processor. So x86, a little bit of history trivia on this. So x86 is actually, what it literally means is something 66. So you know, like you say, X number of days. That's what the X in x86 stands for. And the extension is the first processor, which was 80186, actually came out or was released by Intel back in 1980s. And after that, they started making revisions. So it was 80286, 80386, 80486, and 80586, which was called the Pentium processor. So 80186 was actually 16-bit processor, and from there they started moving on to 32-bit processors. But just for simplicity's sakes, they just kept it x86. So even today, like you will see many applications, they are 32-bit applications. As you can see, even Discord is 32-bit. Does anyone here use Discord at all? Everyone? Pretty much, yeah, okay. Steam uses 32-bit. Who knew? Steam's a 32-bit application, but it downloads all the 64-bit applications, or rather games. They're not 32-bit. Did anyone know that? Also, another interesting thing that Steam, even though it's a 32-bit application, it will actually store all the games irrespective of what bits they are, but they are 64-bit. It will store it in program files x86, which in an ideal world, what Windows essentially meant was all the 64-bit applications will be stored in program files, and all the 32-bit applications will be stored in program files x86. That's why they've got this separation in where they are installed or where they are stored. Yeah, any questions on this? That's actually a very good question. So, yeah, so the way I would sort of think is like if they've, well, they need to reside somewhere, right? So they need to be, because you know, there are certain applications that actually install both 32-bit and 64-bit software, depending on whichever you want to use. So creating those two separation basically just makes sense, like segregation side of things. It's just easier to manage, I guess. Cool. All right. So moving on to 32-bit registers. So these are, okay, so a bit of a homework here. Like you can actually go and have a look at what CISC and RISC is. So complex instruction set computer and reduced instruction set computers. But Intel supports CISC, which is complex. And these are all the registers which are also called, some are called general purpose registers and some are called instruction registers. EAX, EBX, ECX, and EDX, they are also called general purpose registers. So although there's like a specific task for all the registers, which is accumulator register, which store return values from function calls, that's just a general nomenclature. Like that's what the Intel guys want you to adhere to the code, but you can actually use them for like whatever way you feel like. But before I proceed, do you guys know what registers are? Do you want to take it? Okay. Sorry, I just saw you wave, so I was like, okay, all right. So yeah, registers are basically small memory storages built into processors. So the processors actually have these kind of registers so that they can swap the values in and out of these registers. Now, the other alternative for processors to actually store volatile information would be in RAM, which would essentially be in stack. But for every single operation, it's actually very taxing on processors. So because they have to like send data and receive data over CBus channel. So that is a very complex process and it actually takes longer. So that's why they have registers where they can store memory, like store data into the registers and they can just retrieve memory in and out. So the whole purpose of registers is just to provide a quick scratch pad kind of an area for the processor to do its magic. Okay. So yeah, EAX, EBX, ECX, EDX, these are the general purpose registers. And EBP, ESP, and EIP, these are fairly special. I wouldn't say, like, base pointer is okay, but what you essentially would want to control is the EIP and ESP. So EIP is the pointer that points to the next instruction. So if you are to weaponize a buffer overflow exploit or buffer overflow vulnerability in an application, what you essentially want is to make the EIP point to a certain place where your shellcode exists. So your shellcode is something that you want the application to execute, right? So you would essentially want to control EIP to point to that particular area in the stack where your shellcode resides. And that's what will then be executed. How many of you think that this is confusing? So few, geez. Really? Okay, all right. Well, then I'm doing a bang on job. But for those who actually thought that this is a little bit confusing, stay with me. Stay with me. We've got the interesting part coming in about a few minutes, where we'll actually start looking at, building the whole demo yourself, right? Cool. Stacks. So as you probably would guess, stack is it's an abstract data type, which is essentially based on the LIFO model. So a LIFO model, when I say, would be literally like a stack of coins. So the last in, first out. So what you put on last is actually the operation that will be first performed when it's popped out of the stack. All right. Stack, well, since like everything loaded in the RAM is actually in a stack. So whenever a function calls another function, it actually it gets an individual stack frame, which will be spawned, and EBP will then maintain where the process is essentially going to. And when you actually look at stack, if you look at the memory addresses on the left, so the ones starting from 0015 F614, these are memory addresses. So if you look at it this way, it's actually increasing by 4 bytes downwards, but stack actually grows upwards. So the base of the stack would be at the bottom, and it's actually going upwards to a lower memory address. Does that make sense? This was actually hard for me to understand when I was, reading this by myself a few years ago. So feel free to ask questions. Feel free. Still with me? All right, cool. As I said, ESP is basically the stack pointer. So ESP always points to the top of the stack. So can anyone guess, why do I have to trouble the EIP when I can actually make the ESP point to the top of the stack where my shellcode resides? Then why do I bother overwriting EIP? Yeah, so when ESP would point to the top of the stack, and my shellcode just resides there on the stack, so every single time a pop operation comes or happens, then it's going to move downwards where my shellcode resides. Then why do I bother controlling EIP? Is that the base pointer? Okay. I'll let you have a go. Oh, sorry. Okay, so do you want me to repeat the question? Right. Yeah, so EIP essentially is your master pointer. So EIP dictates what you do next. So in that sense, you actually want to control EIP. But what you want is EIP to point to a certain location on the shellcode, and then EIP will do its magic because it will just go sequentially down through the instructions. Okay. Yeah. Yeah. Cool. So I think this will be a better representation of how a buffer overflow exploit looks like. So as you see here, if you look at, if you consider that the car C, or char C, or the way you want to call it, that's the input to the function that we control. And if we give it any more than, to 12 characters, it's going to override or go down into other frame pointers. And this is essentially what we would want to control. So this is how a classic buffer overflow exploit would look like in the memory. Does that clear a little bit? Well, no, so yeah, so that's what I meant. So ESP is not, well, ESP, the purpose of ESP is actually to point to the top of the stack. So ESP in reality doesn't do anything. It's the EIP that points to the next instruction that the processor should concentrate on. So overwriting ESP doesn't mean anything. It doesn't. Well, ESP? Or, okay, so ESP, the use of ESP is to provide the stack frame where it's currently executing or where the EIP is currently at. And you've got the base pointer, which is essentially your return stack. So like I said, every single function gets its own stack frame. So if there is a main function, so think of it this way, you've got, like in a standard C program, you've got a main function, right? And then you create another function that does something else. So you would have a main stack, and then you would have a stack for another function. So when you call or when your function calls another function, then it actually gets its own stack frame. So it will move to a different stack. But then the processor needs to know where to go back to once that function's executed and once that's done. So that's the purpose of eBP. It provides the base pointer for the stack to return to where it was. So ESP would point to the top of the stack. Sorry, did I answer your question?
Not exactly. So the EBP is to return to the previous stack frame.
Yeah.
But the ESP stores the top of the current stack frame. Right?
Yeah.
So that's what's stored in it, but what actually reads that and uses it? What is its purpose?
Okay, so that's actually a very good question. I may not have the right answer to it, and I don't wanna take a guess. But yeah, I'll look it up and I'll talk to you about that. Yeah.
Can I try and answer his question?
Sure.
Okay.
Or is it the ESP?
The return address would be EBP. So EBP will. Okay. So what I would encourage you to do is write a simple program, assemble it, make it an executable, and then disassemble it in whatever disassembler of your choice, IDA Pro, whatever. Once you start looking at it, you'll actually notice that there are certain prologues to every function. So a prologue would be certain sequence of instructions that essentially dictates, okay, all right, so I'm going to push EBP, then I'm going to move ESP into EBP, and then I'm going to call ESP. So these are a certain set of instructions that actually defines, okay, if I just look at the assembly, instruction set, or if I look at the assembly disassemble code, then I can actually make sense, okay, if I see these 3 set of instructions, that means that that's actually a function, right? And then there's an epilogue, which means it's going to clear ESP, and then it's going to move EBP into ESP so that ESP can then point back to where it came from, right? So I would encourage you to do that if you've got any doubts. Like I said, this is not going to be like a white paper research. It's just to get you started. And then if you've got any questions, feel free to reach out to me, or you can actually look it up, because in that process you will learn heaps. Sorry, yeah. In a way, yes. In a way, yes. All right, cool. Anyone, any questions so far? Going once, going twice. All right, cool. Okay. So the way we generally approach, writing buffer overflow exploits or writing exploits would be, firstly, you identify a crash point in an application. So crash point would be you'd fuzz the application with varied length of input, and just to observe where the application crashes. And then you identify what's overwritten. So what overwrites into EIP, where does our shellcode lie on the stack? And then we check the location of the shellcode, essentially the point where the shellcode starts on the stack. And then we've got identifying bad characters. So bad characters would be, even though it's called bad characters, but I would essentially call it a restricted character set, because every single application has its own character set that it can handle or it can work with. Bad characters are basically those characters which would be outside its normal use or normal usage, which will cause the application to respond differently. And then jump to shellcode would be, you would force the EIP to jump to your shellcode, where you'll start executing the shellcode. And then you've got popping calcs. So because we're the good guys, we're not going to do reverse shells. We're just going to do popping calcs. All right. Cool. So your target for today is download the software from that particular location.
Okay. First thing we're going to do is download a copy of the vulnerable application from that link. So we're going to go to exploit.db.com, exploits, and 10374. So this is a written exploit that somebody's published for this program, but since we're going to be writing one ourselves, we're just going to go to this vulnerable app link and grab a copy of it from right there. Once you've finished downloading it, just run it, install it, go through everything default, and once it's successfully installed, you should have a copy of a link to it on your desktop. And if you run it, we should be able to load up files, run stuff. It should be able to run. Next up, we're going to grab Mona, which is sort of like a so github.com/callland/Mona. It's a bit of an extension pack for the immunity debugger. It gives us a whole bunch of commands that will be really useful in our exploits. So yeah, once you've got it downloaded, extract that and jump into the folder. All we need to do is grab this mona.py file because that contains all of the magic. If we go to C drive, programs 86, immunity inc, immunity debugger, and the py commands folder. Just chuck it here, and we're good to go. All right. So step one, we need to identify the crash point. So if we run the program, we can see that we are able to load files into the program. This essentially means that the program will accept a user-controlled input and try to process it. So in this case, we're trying to load in a file. The program will have a certain size, of the variable or buffer in memory that is going to try and hold the data of this file is a certain size. If we can pass it enough information to fill up that buffer and then go past and overwrite more memory outside of the allowed bounds of that buffer, then we may be good to go. So the first thing we're going to do is try and find the crash point for that program. So this is going to be our starting script, the building blocks of our exploit. So let's kick it off. So right here we've got buff equals x41. So this is just the character in hexadecimal code that represents an A. And we're going to multiply that by 20,000. And all that's going to do is generate Yep, so we're going to set it with file name, call it evil.m3u, because that's the m3u is simply just the file extension on the file, so that this program will recognize it. And then we're just going to save that to the file, evil.m3u, write it, and then close it. So we're going to save this. I'm going to use the My Documents folder and I'll create a demo file folder and call it as my working directory. So now that we have the script saved, I'm just going to have to run it. So I'll browse to there, Documents, Demo, you can see it there, and I'm just going to run that. Now, if this doesn't run properly, you may need to double check your Python setup. You may be running a wrong version of Python, or you might be running the 64-bit version of Python. So let's just go have a look at what that's created. Here we go, evil m3u. So just to show you what I mean, just to prove what, yeah, we can see that the data for this file is nothing but 20,000 A's, just absolute trash. So we're going to just chuck it in the program and see what happens. And we're going to run it, and that didn't work. So it threw, this is a exception that they've clearly written into the program saying failure in loading this file. So it handled that well. The program's still functioning fine. It just said no, the file's not going to work because it's not valid. So let's try again. Let's bump it up this time. I'll have a go at 30,000 A's. So I'll save that. I'll run this to generate the new file. I'll go load and run it. And that's what we're looking for. So the program has crashed. This likely means that we've overwritten some parts in memory that the program needs to function, and it's just fallen on its face. So we know that the crash point is somewhere between 20 and 30,000. 20 and 30,000. All right. Let's open Immunity and get into the debugging. So this may, if you've never used a debugger before, this may be somewhat intimidating, but don't worry, it's pretty simple once you get your head around it. So the top left pane is a CPU pane. So this is the assembly code of the program, all of the assembly code of the program and the instructions that the CPU will try and step through as the program executes one by one. Bottom left is just a hex code. It's just a hex dump of the program's, the executable file. So that's not going to be very useful for us today. The top right is where the, so these are the registers in the CPU that Viren was talking about. So the EIP, that's the instruction pointer, and that points to the that points to the memory address of the instruction that's currently being executed. I kind of like to think of that as someone who's reading a book and just pointing their finger along each word as they go along, and that's kind of how that works. And then there's the ESP as well, which will come in handy later. The ESP just points to the top of the stack, so the memory address that is at the top of the stack. And then the bottom right is our actual representation of what is on the stack, and the memory address is there. So let's open up the program. So if we hit open up in the top left, and we can find our desktop shortcut, we can load up the program. All right. So we can take a look. The EIP is currently pointing to this memory address and this first instruction, and the ESP is pointing to the top of the stack right now. So this is the address that is right at the top of the stack. So we're just going to run this program by hitting, you can hit the play button up here, or you can hit F9, and this moves down to the entry point of the program. And we're just going to hit F9 again to let it run. Now you can step through all of these instructions one at a time, and you can set breakpoints if you find a spot where you want it to stop, and the program will run through until it hits that breakpoint, and it'll stop and wait for you to do something. But for now, we don't really care. We're just going to let it run through as it normally would execute. And since it's been run, you should see an instance of the program up and running. And we're just going to load our dodgy MP3 file into it again. So we're going to run that. And here we can see just how much damage we've done. So we can see an access violation while trying to execute the memory address AAAA, which obviously doesn't exist. So we can see that we've overridden the ESP, because that's just pointing to A's. The ESP right here, it's completely overwritten with A's. The EIP as well, it's completely overwritten with A's. So the first thing we're going to try and do, so we can see what's overwritten, what's loaded onto the stack. It's a shitload of A's. Now what do we do? So we're going to be using this Mona extension, which is extremely helpful. You can do a lot of what Mona will do manually, but it will just save a crap load of time. So the first thing we're going to do is set the working directory so that Mona knows where to save all of the files that it's going to dump. So we're going to go Mona config set working folder, and I'm just going to chuck it to be the same address as this. Now note, if you have any spaces in your path, it might screw things up. And from my very short experience with Mona, it doesn't seem to like wrapping stuff in quotes. It still seems to sort of cause some issues. So I'll just recommend not using a path that has any spaces in it. So cool. So the first thing we need to do is figure out what the offset is that brings us to this address. So we know that we can dump a crap load of A's into here, but we want to figure out how many A's we have to dump into the program to reach this point. And once we know exactly what that point is, we can start writing exactly what gets written into memory here. So we can remember our goal is to control the EIP. So we want to point this towards our shellcode. So the first thing we're going to do is create an offset. Create a pattern. So the most brutal, like caveman sort of way that we could approach this is say, we know that the crash point is somewhere between 20 and 30,000. We could go through trial and error trying to replace stuff between 20 and 30,000, or we can use Mona to create a unique pattern. So we'll give that a go. So we're just going to go Mona pattern create, and we'll say 10,000. So this creates a pattern of 10,000 unique bytes. Here we go. So pattern. So this is a pattern of 10,000 completely unique bytes, and here it is in hexadecimal for us. So what we can do is we can append that to the start of our shellcode. Yeah, let's just do it. So we're going to grab the hexadecimal values. We're going to bump this back down to 20, and then we're going to append this to the end. So we're going to go buffer plus equals and chuck that in there, and that double exclamation mark. So we have 20,000 A's and then 10,000 unique characters. So we're going to save that and give it a run. Now we're going to restart the program by pressing Control F2 and going yes. And we're back to the start. So we're going to mash F9 twice again and let the program run through. Load in our new file. And now we can see that we don't just have a crap load of A's, but we can actually use these characters to figure out how far down it actually was. So we're going to see the EIP is 37754,836. It's 37754,836. So the EIP is actually at this memory address. But what we can do is we can say we don't just instantly see it. We can go Mona pattern offset, and we can pop the EIP in there. And so we're looking for the offset of the EIP, and it's going to say, hey, we found this at position 60, 80, 377, 54, 836. 377 54836, and that's so. What we can do is we can find exactly where how far down that is. Now, remember that this is going to be in little endian format, so that'll be covered in a later slide. But all you need to know for now is that when data is written to the stack, it's in little endian format. So that means the bytes are organized in we're going to search for this, we're going to have to go 36. So it's 1 byte at a time, but it's reverse. So we have to go 36, 48, 75, and 37, which might be a little bit confusing at the moment, but we'll get there. So I'm just going to search for those. X36, X48, X75, and X37. So this is how far we need to go down to overwrite the EIP. So if I kill that, I can see that it's at column 24329. So that means that it's 24329 characters in 24329. So 24329. I'm going to get rid of 1, 2, 3, 4, 5, 6, 7. I'm going to minus 8 from that, because I'm just trying to find out how many characters along it is. So it's 24321 characters along, and I'm just going to divide that by 4, because each byte for us is made up of 4 characters. So now it's about 6,080 characters across. Just to verify it, Mona got it right the first time. So when we said, Mona, what's the pattern offset for the EIP value? it went, it's 6,080 characters out. So that's pretty certain. So what we can do now is we can go 6,080. So we're pretty sure that if we override it with 26,080 A's, then whatever comes next will be written straight into the EIP. So I'm just going to comment that out for now. And maybe we can just prove that by grabbing some of this. And I want to say buffer plus. Let's just verify that we got it right. So we'll save that, run it, restart this. So we can see that we've written up to here, and the EIP is written with 61413161. If we look at our shell code, 6131. So if we look at it in Little Endian, so this 61 maps to this 61, and then 41 to 41, 31 to 31, and 61 to 61. So we've successfully overwritten the EIP, which is great, which means in theory we can now point the program towards any memory address and get it to execute that, the code that is there. However, before we go dumping in shellcode and telling it to execute it, we need to identify bad characters. So the bad characters are pretty common. Most applications are not able to use any Unicode character as input. If there are characters that are incompatible with that, the program will either crash or not, or throw a. I guess the program will crash, but it won't allow us to execute our shellcode. So, for example, the character x00, which is a null byte, is almost completely incompatible with most programs. So it means in the code, in our exploit shell code, we cannot use this character. We need to exclude that in anything we do. But often there are other characters as well. So before we can try to exploit this program, we need to figure out what all of the bad characters are. So what we can do now is basically the easiest way to find this is to basically generate a list of every character that there is, throw it into the program, and you can just see which ones get saved into memory. If it reaches a point down the list and the address just doesn't appear in memory, then it means the program was probably not able to pass that character. So let's get rid of this. And we want to do it right onto the end of here. So what we can do is say, hey Mona, give me a byte array. And since we just assume that a null byte is going to be bad, we can say bad characters x00. So it'll give us an array of all possible characters, but it'll exclude the null byte. Yep. And there we go. That's all we need. So close that off. I'm going to open the byte array and copy paste to this. I'm just going to do a bit of sneakiness, so I want to replace that with buff plus equals. I'm going to start up there, and I'm just going to mash F. So I'm just pressing F and R to alternate it. So I've replaced all of the first double quotes with the buffer plus equals. And we're going to pop that in here. So our buffer will now contain 26,080 A's and then an array of all possible bytes. So let's just save that and generate it, and we will start it again. So all right, I'm going to load it in, and let's see what we've got. So at this point, we can see that this is the start. So we started off with 1, 2, 3, 4, 5, 6, 7, etc. So we're starting from the right to the left. We can see 1, 2, 3, 4, 5, 6, 7, 8, 0. So that means whatever was next after 8, 09, that's probably a bad character because that caused it to just go to shit. So I'm just going to make a note down up here. X09. We're going to remove that. And now we're going to try again. So, sorry, the null byte is also a bad character. And so I'm going to show you this other function that Mona has that makes our life a little bit easier. We could keep going through it one by one and trying to eyeball it, but what Mona can also do is so I'll add that to our 09. If we generate a byte array, we notice that Mona actually creates a byte array.txt and a byte array.bin, and it's just a binary file of all the characters. I'll restart. So now our new byte array.txt is missing the 00 and the 99, same as our shellcode. So I'll pop it in, and we hit our crash point. So what we can do instead of going through and eyeballing it bit by bit, did I save it? Because it crashed at 9 again. I might have to do that again. So I'll save, run, start again. And poof. So what we can do is we can say, hey Mona, compare path to file. Alright, to use this compare function, first we're gonna need to, because we need to give it an address, I want to give it the ESP address. So we can see that we're overriding from this point at the moment, so I'm just going to add 8 bytes to the offset so that we can overwrite the ESP, and then we can get the function to work from there. So I'm just going to add 8 bytes here, save that. Restart. So we can see that we've started overriding from the ESP at this point. And rather than trying to figure out by ourselves, like one bit at a time, we can just say Mona compare file, and we're going to feed it this bin file, byte array.bin, byte array.bin, and we're going to give it an address to start at, and we're going to say the ESP. So that will search from this point onwards for bad characters, which will be very helpful. So after 8 bytes, it's had a problem. So it thinks the bad characters so far are 00, null byte, 09, and OA. So let's try that. We'll add OA to our list of bad characters. OA. That's right here. Save that. Give it another run. Just restart. Alright, I'm going to have a click. This looks a lot better, so we can see 1, 2, all the way through. Still good, still good, still good, and we've reached the end. The last one we saw is FF, which, if we look at our array, is the last character. So if it's successfully been able to pass all of those characters, then that means we've found all of our bad characters. So in whatever shellcode we generate, we have to emit 00, 09, or OA. Now that that's done, we can jump to the shellcode. First off, let's generate some shellcode actually. So I've got my Kali VM here. I'm going to use MSF Venom. And we can list payloads with, if you want to check out the commands, msfvenom.h, you can go in msfvenom list and payloads. And you can use the list command to list just about anything else there is. We're not going to do that though, because we're just going to use the payload Windows exec, and this payload simply executes a command in Windows. We're going to set the command parameter to be calc. It's commonly used just as a proof of concept. If you can force Windows to execute the calculator program, that means you can force Windows to execute anything. We're going to grab it in Python format because I want to be able to chuck it directly into our Python exploit. And we're going to give it the bad characters as well. So we're going to say B. We're going to tell it to exclude 0, exclude 09, and exclude OA. And so this will generate us some shellcode that will avoid using those characters that we can use. Boom. So we're just going to grab that, swing back over to our program, and we're going to replace this good stuff with shellcode. So this offset currently drops down, overrides the ESP, but we want to go back to overriding the EIP, so we're going to get rid of those extra 8 that we added. Now, so we know the ESP is at this address, and we can write anything we want into the ESP. We know that EIP gets to this address, and we can write anything we want into the EIP. So if we are able to write our shellcode starting at the ESP all the way down and write this address into the EIP's value, so that when it gets to this point, the EIP will jump to here, and then these instructions will be executed next, and the program will execute our malicious shellcode. Then we're good to go. However, we've got a problem here because the null byte in this memory address is going to be an invalid character. So we can't just pop this address directly into there. So we need to find another way to jump to this address. Fortunately, we can just say Mona, give me addresses for any time there is an instruction that jumps to the ESP. So we can run that and go to that window. And we can see here that at these memory addresses there are already instructions that jump to ESP. So we can just borrow one of those. At this memory address here, so these contain null bytes, so they're going to be useless to us as well. However, this one right here looks valid enough. So x58 and xb0 x01 and x10 0110 58 b00110. So we save that and let's see what happens. Cool. So we now see that our EIP is now pointing at this address, and that ESP 614 615 So our EIP is right in here somewhere. So we've successfully jumped to the ESP, and the final thing we need to do is add what are known as NOP characters. This is an instruction that the CPU it's represented by an X90. So this is adding one NOP character, and when the CPU is given a NOP or an X90 or a 90, it's basically an instruction that tells the CPU don't do anything. Just don't do anything and pass along to the next instruction. So if it hits a NOP character, it will just go down one. If it hits another NOP, it'll go to the next instruction, and etc. All we need to do now that our shellcode is ready to go, we just need to pass it several NOPs, which is known as a NOP sled. You chain several NOPs together, and that will tell it to pass down until it hits our shellcode, and then it should execute our shellcode. So we'll just give it 20 NOPs to be safe, and we'll save that. And go again. And boom. Program's still running, and we've successfully executed a calculator. Now you might be thinking, why is that so bad? It's just opening a calculator. I'll give you an example that shows that having code execution on a machine is pretty bad. So rather than a benign calculator payload, what I'm going to do is instead replace this with a interpreter payload. I'm going to tell it to call back to this IP address and the only port that a hacker can use, and Python, and exclude those bad characters. Over here I'm going to start up Metasploit. Oops. I'm going to fly back, and we're going to replace our benign shellcode with some slightly more interesting shellcode. And all we need to do here is start up the listener. Never press tab. There we go. Now we're listening for incoming connections, and if we now passed somebody who was running this program a certain file of ours, or we tricked them into executing it, boom, we have a shell. And that's bad. So that's about it for this tutorial. I mean, a lot of concepts, if you're looking at this kind of stuff for the first time, a lot of these concepts will take a while to wrap your head around. And yeah, it's to be honest, I'm still trying to wrap my head around a lot of it. So the jump to ESP, I only just sort of figured out why we need to do that, but the NOP sleds, I still don't know why. I just know that we have to. So everything that you aren't sure about, like Viren said in the presentation, all you can really do is, well, the best thing to do is look it up yourself. Start Googling, start researching, start trying to wrap your head around concepts. If there's a term or a phrase that you don't 100% understand, keep searching until you do 100% understand it. And so this difficulty curve gets a lot easier. Once you've wrapped your head around the basics of this this kind of stuff, it will get a lot easier for you. So it's not going to be this daunting forever, but you just have to get over that first hump. Here's a few links that Viren left. Unfortunately, we didn't record the questions at the end, so if you have any questions, Google's your friend. But thank you for watching us through, and I hope you guys got something out of it.